From the engine in your car to the frame of your phone, our entire world is basically built from these perfectly shaped bits of metal. But have you ever stopped to think, how do they do that? How do we get those perfect shapes? Well, today we're going to dive into the hidden science behind carving metal.
Okay, just look at this thing. Believe it or not, that started out as just a boring, solid cylinder of metal. So the question is, how on earth do you transform that into, well, this? Something so incredibly detailed, with surfaces that are perfectly smooth and measurements that have to be just right. Well, the answer is a process called machining. It's a kind of subtractive manufacturing. And really, it's like being a sculptor, but for metal. You start with a block, and you just carefully take away everything that isn't the final part. You're revealing the shape that was hiding inside all along. Now, from a distance, it kind of just looks like you're peeling an apple, right? Just shaving off bits of metal. But if you could zoom way in, right to the exact point where that cutting tool touches the workpiece, what's happening there is frankly an incredibly violent and super complex event. So to really get what's going on, we have to go microscopic. I mean, you've got this insane amount of pressure, friction, and heat all happening in a space smaller than a grain of sand. It's chaos. So for engineers to even begin to understand it, they have to simplify things. They build models that break all that crazy physics down into something we can actually wrap our heads around. Okay, so here are the two main ways they think about it. Over on the left, you've got what's called orthogonal cutting. The easiest way to picture this is like a perfectly straight razor blade slicing into something. It's a clean 2D model. Then, on the right, you have oblique cutting. Now, this is what happens most of the time in the real world. It's 3D, and the cutting edge is coming in at an angle. So to really get to the core physics of this, we're going to stick with that simpler version for a bit, the orthogonal model. Because if we can understand what's happening in this clean 2D slice, we can pretty much unlock the secrets of what's going on in any kind of metal cutting. All right, let's zoom in. Welcome to what's called the deformation zone. And honestly, microscopic battlefield is the perfect way to describe it. This is the exact spot where a solid piece of metal is literally forced to tear itself apart, to shear and deform until it becomes what we see as a metal chip. And what's so cool about this diagram here is that it shows us that this battlefield is actually split into 3 distinct zones. You can see them right there, all huddled around the very tip of the tool. The primary, secondary, and tertiary zones. Each one has a very specific job to do in this whole process of tearing the metal away. This is where all the action happens. So let's walk through it. First up is the primary zone. This is where the metal in front of the tool gets sheared and literally bent up and poof, it becomes the chip. But it's not over. Immediately in the secondary zone, that new chip gets squashed and dragged right over the top of the tool. That surface is called the rake face. And then finally, you've got the tertiary zone. That's just where the side of the tool rubs against the brand new shiny surface that's just been cut. And check this out. This shows you just how intense the friction is in that secondary zone we just talked about. The pressure is so unbelievable that for a split second, the metal chip literally welds itself to the tool. They call it the sticking zone. Only then, once the pressure drops a little, does it start to slide off. Isn't that wild? Okay, so you've got shearing, you've got welding, you've got sliding. You can just imagine the insane forces that are at play here. So the next big job for an engineer is, how do you map all that out? How do you predict those forces with any kind of accuracy? Now, I know this looks a little intense, but don't get scared off by all the arrows. The best way to think about this isn't as a math problem, but as a map. It's a force map. It's just showing us all the different ways the metal is pushing and pulling on the tool, all at the exact same moment. It lets us see how everything balances out. So let's just point out the big ones on this map. First, you've got the tangential force. That's the main muscle, right? That's the cutting power coming from the machine's motor. Then you have the feed force. That's the push that's driving the tool into the material. And when you add all these up, you get the resultant force. That's basically the total amount of stress the tool is under. Now, you can bet there's some heavy math behind a map like this. Engineers have these powerful equations to figure out everything. The stress, the strain, even the exact temperature right at the tip of the tool. And this isn't just for fun, it's not some academic exercise. The whole point of all this math is to get perfect, repeatable control over the cut every single time. Okay, so deep breaths. Let's zoom back out from the microscopic world. How does all this physics, all this stuff happening at the micron level,
translate to the huge, powerful machines we see on the factory floor, the ones that actually build our world.
Here's a great example. This is a lathe. A lathe puts all those principles to work by spinning the piece of metal really, really fast. And then a stationary cutting tool just carefully moves in and shaves away the material. It's perfect for making anything round, like shafts or pins. And then you've got this, a milling machine. It kind of does the exact opposite. On a mill, the workpiece stays put, and instead, a spinning tool with multiple cutting edges moves across it. This is how you get flat surfaces or cut out pockets or create really complex 3D shapes. So, you might be wondering, how do these giant machines have such fine control over that tiny microscopic cutting action? Well, a key piece of tech is something called a digital readout, or DRO for short. It's basically a system of super precise sensors that tracks the tool's position down to 1/100th of a millimeter. We're talking about a measurement smaller than the width of a human hair. It gives the person running the machine absolute pinpoint control.
All right, so we've been on quite a journey, haven't we? We started with the finished part, zoomed all the way down to the microscopic level, and then zoomed right back out to the machines on the factory floor. So what's the big idea here? What should we take away from all this?
It's this. The next time you run your hand over a smooth, polished piece of metal, I want you to remember that it's not just a simple surface. What you're feeling is the end result of a tiny, incredibly energetic, almost violent event. An event that has been completely understood, tamed, and engineered with microscopic precision. Everything we've talked about today, all this amazing science, is about one thing: removing material, subtracting it, with absolute precision. And that leaves us with a really fascinating question for the future, doesn't it? What happens when we get just as good at adding material with that exact same level of control?